Okay, we'll go on now to the next topic, which is really a continuation of the quadratic equation, but applied now to an RLC network. Now, as analog signal processing designers, maybe you say you don't care about RLC networks because you never use inductors. For very good reason, of course. In modern components that are available, the tremendous advances we've seen over the last 20 and 30 years arise first because of ICs, and then after that the various generations that followed, leading to greater and greater density of components on the chip, more and more function that it's capable of as the components get smaller and smaller. And all that results because of the breakthrough of being able to put R's and C's on the same chip along with the transistors. The inductors got left out. They never got onto the chip. So they remained outside, huge, bulky, expensive, and totally incompatible with everything else that goes on the chip. So signal processing designers learned very early on, never use inductors, certainly not transformers. In fact, the evolution seen from the student point of view is digital took over. You can hardly even find analog designers anymore. This is probably the largest number ever gathered in one room right here. So, same thing happens with the Caltech students. They come in as freshmen and they take their first digital lab and they become instant digital nuts. They want to spend the rest of their undergraduate years connecting together these little black boxes. And there's nothing wrong with that. It just isn't electrical engineering. Ones and zeros are very important, but eventually analog comes back in because the digital people push the clock rates higher and higher, and eventually they have to acknowledge there is, after all, something in between 0 and 1. And what prevents you from making that transition vanish is the old nemesis L di by dt. You can't change things instantaneously. So even the digital people finally have to acknowledge inductance, and the analog people finally have to acknowledge it anyway at high enough frequencies, because then trace lengths stop becoming important, and you have to remember that other basic rule of thumb: the inductance of a piece of wire is around 10 nanohenries per centimeter. So that's a useful thing to remember. Anyway, the fact that you don't use discrete inductors doesn't mean that you don't have to worry about R's, L's as well as the R's and C's. And you have to worry about it for another reason as well. That the mathematics that goes with the RLC circuit is identical with the mathematics that goes with loop gains and stability margins and feedback systems, in spite of the fact there may not be an inductor in sight. But the algebra is still the same. So all of this is by way of hope persuading you that understanding what goes on with a basic RLC network is still important. Even though, as signal processing designers, you may want to simulate an inductance by using a couple of op amps and some integrated R's and C's, but still you have to remember that what you are simulating is L di by dt, and you are not simulating 1/2 Li squared, the energy content of the inductor. Now, if you're a switching power supply designer, you have to use real inductors. You can't simulate them because it's the energy storage content that you need to use. in a switching power supply. So that's why power supply people work with a different set of components. Instead, they hate resistance. Resistance is lossy, spoils the efficiency of the switching power supply. So switching power supply designers use L's and C's and switches. Signal processing designers use R's and C's and linear operation of devices. It's a different game altogether. And that's the first thing to recognize, that designing a switching power supply is no longer a simple extension of analog design as it used to be in the days of linear power supplies. That's been part of the reason why switching power supplies have always been neglected. They're always at the end of the priority list. All the interesting stuff is in the signal processing, and you get all that part done, and then you suddenly realize, oh, we need a power supply for this. And there's a funny shaped corner left in the box, and that's where the power supply has to go. So, and who shall we give it to for design? Well, here's this new fellow who's just out of school. He isn't doing anything very important yet, so he can do the power supply, because that's trivial anyway. Well, unfortunately, in the case of switching power supplies, that isn't true. And you spend a lot of time at Caltech getting the message across to students that to be a specialist in switching power, you actually have to be a specialist in a whole lot of areas that most people are quite happy to be a specialist in only one of them. Because you have to know about signal processing anyway. You also have to know about some fairly complicated control problems, because a switching converter is a nonlinear device and you're going to put a feedback loop around it. So aspects of modern control get into it. And of course you have to know a lot about magnetics that no one else wants to know anything about. You get students coming out of school now who think that a transformer is N1 to N2 and that's all you have to know about it. So this switching power design is a whole different field. You have different objectives and you have a different selection of components to work with. Anyway, we don't want to get into that sideline right now. We're talking about the basic RLC circuit, and the first thing we want to know about it is what's its voltage transfer function, V2 over V1. Treat it as a voltage divider, and in one line you get the basic expression, which is now a quadratic in complex frequency in the denominator, and the numerator remains 1. So now here's the first thing you do whenever you see a quadratic. You define a corner frequency and a Q factor. The corner frequency is by extension of what we did with the single pole function. It's the coefficient of the highest power of S. So you define 1 over LC as being the square of the normalizing frequency omega 0. Then you put the middle term with the same normalization, and what's left behind in the coefficient of the middle term is dimensionless, and you call that 1 over Q. And having done it in that way, you find you can write the Q in various different combinations. One version of Q is it's the inductive reactance at the corner frequency divided by the series resistance. Equally well, the Q factor is the capacitive reactance, 1 over omega 0 C, divided by the series resistance. That follows because the inductive reactance and the capacitive reactance are equal at the corner frequency by definition of the corner. The third way of writing it is simply identifying what those two equal reactances are. So you write them, either one of them, as simply R0, because they have the dimensions of resistance. And in terms of the original element values, the R0 can also be written as root L over C. And it has a name, which is the characteristic resistance. Of what? It's the characteristic resistance of the L and C. In other words, it's a property of the L and C, and has nothing to do with the R. And that name is by analogy with transmission lines. In a transmission line, you have a distributed L and C per unit length, and it has a characteristic impedance, which is the square root of L over C per unit length of the transmission line. I never understood why it was called impedance when it's really a resistance. But I didn't choose the name for transmission lines, but I've taken the liberty of choosing the name when it's a lumped transmission line, where you have a lumped L and C, and the characteristic resistance is root lumped L over lumped C, and it is a resistance. The important thing is that we have two parameters, corner frequency and characteristic resistance, which are properties of the L and C only. In other words, they are substitutes for the L and the C. It turns out that since the transfer function of the network can be expressed in terms of those two parameters, they take the place of the original L and C. In other words, what's important about the L and C is not the number of henries and the number of farads. What's important about them is what corner frequency does the combination have and what characteristic resistance does it have, because that determines the nature of the result. The third parameter, the Q, is the only parameter that gets the real resistance into it. And you see by this simple definition that the Q factor is the ratio of the characteristic resistance determined by the L and C to the actual resistance of the circuit. That's the only place the R gets into it. Now, once we've defined these parameters, omega 0 and Q, we have now a normalized quadratic, which is like the one we've just been talking about, where the A is 1, the C is 1, because we've normalized the frequency as well, and the B has become 1 over Q. And the Q is now the remaining parameter that determines whether you have complex roots or real roots. You knew that already. But now we see the real reason why there is only one parameter that determines the nature of the results. Well, now that we have these two roots, omega 1 and omega 2, let's look at what some typical shapes are for the magnitude and the phase of the quadratic transfer function. The way to start, again, is to look at zero and infinite frequency asymptotes. If S goes to 0, the function goes to 1, so we have a 0 dB flat gain at 0 frequency. Go to the other extreme, as the frequency goes to infinity, it becomes a 1 over omega squared function. So that is a double negative slope, minus 40 dB per decade. So the asymptotes now look like that. Here's the 0 dB zero frequency one, here's the 40 dB infinite frequency one, and if you extrapolate them to where they intersect, they again intersect at the corner frequency, because that's where both asymptotes have the same value, namely unity. All of this is independent of the value of Q. Q only comes into the act in determining how the actual function goes through the corner. So when you look at the magnitude function, now the magnitude of this complex function of frequency is, as usual, 1 over the square root of the sum of the squares of the real part and the imaginary part. And the special case, if you evaluate this function at the corner frequency itself by putting omega equals omega 0, the magnitude is equal to Q. Because the square bracket goes to 0, this coefficient goes to 1, and you simply get the square root of Q squared in the numerator, which is Q. Which means that the value of each green line as it crosses the vertical line at omega 0 is the value of Q belonging to that particular curve. So that's the Q of the top one. This is the Q of the second one. That's the Q of the third one, and so on. Very simple. Not many people know that. Very useful to know. Notice that the value of Q is not the maximum. The maximum is a little bit to the left. If Q gets to be very large, then the maximum becomes essentially the value of Q, but for lower values of Q, the maximum moves to the left a bit. And when Q is getting close to 1, actually that maximum moves so far to the left that it disappears off the picture, because when you get a Q of less than 1, there isn't a maximum. Well, I purposely left out the interesting case in between. What happens if Q is exactly equal to 1? That means that the green curve that corresponds to Q of 1 goes right through the asymptote intersection. So I can mark that point Q equal to 1. What does the green curve look like? Does it have a sharp corner? No, you know it isn't going to have a sharp corner. No real function does. What happens is the maximum is now pretty far to the left, and the actual curve goes through the corner smoothly, but it bulges up a bit on both sides. If I superimpose the maximum as well, that's gradually moving to the left. Now, you see, you can divide the general result into two classes, and you can choose two different dividing lines. A Q of 1 is a convenient dividing line in the sense that it separates characteristics that have a significant peak from those that don't. A Q of 1 is sort of the sharpest corner that you can get without having much of a peak. So if that's a criterion in your design, a Q of 1 is a good way to characterize it. That's a little different from the other way to divide the two cases, which is a Q of 0.5, which separates real from complex roots. So a Q of 0.5, of course, is less than the 1. So this curve I've drawn next below it might be a Q of 0.5, which means it would go through the point minus 6 dB at the corner frequency. That separates complex roots from real roots. So you could say the dividing line is sort of fuzzy depending on what your criterion is, which is more useful from the design at hand, whether the roots are real or complex, or whether you want the sharpest response without much of a peak. Okay, this is the standard handbook version of the generalized second order response in terms of Q factor. And of course, you want to know what the phase graph does at the same time. So let's construct that. The phase is again minus the arctangent of the ratio of the imaginary part of the quadratic to the real part. A little more complicated this time. Again, simply approach it by considering zero and infinite frequency asymptotes. At zero frequency, arctangent of 0 is 0, so you get a flat phase asymptote of 0 degrees. At the corner frequency itself, omega equals omega 0, the denominator goes to 0, arctangent of infinity is minus 90 degrees, so the phase graph goes through minus 90 at the corner. For higher frequencies, the function gets small again as you go to infinite frequency. Arctangent of 0 coming in from the negative direction is minus 180 degrees. So again, you get a flat asymptote at infinite frequency. And again, all of those properties are independent of Q. So the phase always goes from 0 through minus 90 to minus 180. And the only difference that Q makes is how sudden is the transition. So for one value of Q, you might have a picture that looks like that. And the only thing that changes is the slope as you go to different Qs. And the higher the Q is, the steeper the slope. It's also antisymmetric around the corner, just like it was for the minus 45 per decade for the single pole. You don't need both of those together. And once again, it would be nice if we had an approximate straight line which we could draw in order to match the actual transition. Now we can approach that in the same way that we did for the single pole function, except that there's not a unique line this time, because we're going to get different lines for different values of Q. But a starting point, once again, would be find the slope of the actual phase graph at the symmetry point and extrapolate that slope until it intersects the other asymptote. And then by geometry, find out what the value of that frequency is. Then, when you want to draw the straight line, you just mark off that frequency on the horizontal axis and then draw your line. Well, it's pretty easy to do that little calculation. You find the slope of the arctangent function at the symmetry point and extrapolate it, do some geometry. The only catch to that is how to do geometry on a semi-log scale. And it's a useful little workout for you to try doing that, actually. The result is a little odd in appearance. The ratio of this intercept frequency omega I to the corner frequency is this rather peculiar number. E to the pi over 2, which is just a number, happens to be 4.81, raised to the power 1 over 2q. E to the pi over 2 isn't an easy number to remember, and in addition, I don't like it. It's pretty close to 5. Why don't we call it 5? What happens if we do? If I use 5 instead of 4.81, then this intercept frequency moves out a little bit. What happens? The slope of the asymptote gets slightly shallower. And again, just as in the single pole function, it turns out we get a better answer anyway. Because now, a slightly shallower line means that we're not matching the slope at the maximum point, and we've split the deviation of the actual curve into two sides instead of having it all on one side, which means the maximum error of the straight line from the actual curve will be smaller. So not only do we get an easier number to remember, 5, but we get a better answer anyway. It isn't often Murphy's law is confounded. Accidentally, we get a better answer by making an approximation. Okay, this is a useful thing to remember then, as to how to make an approximate straight line asymptote representing the steepness of the phase transition for a quadratic function. I've never seen this in any of the books. Even with the 4.81, I haven't seen it. And yet it's an obvious completion of the symmetry between the single pole function and the two pole function. All the books have got minus 45 per decade in it for the single pole. Why don't they have this? It's easy enough. But for some reason that little gap never got filled in. So you might want to add this again as an extra page in your handbook of useful things. Well, now we talked about both the magnitude and phase for the quadratic function. Let's relate this to the solution of the quadratic that we've talked about already. Here it is in the format that we've derived it for the RLC network in terms of the corner frequency and the Q. Here's the similar form in terms of the A1 and A2 and the X variable of the quadratic. There's two ways you can write that. One of them involves normalizing the X to the corner frequency. The other involves not normalizing the X and just keeping the original A1 and A2 coefficients. In either case, you can define this f function in terms of the A1 and the A2 or in terms of the Q. Notice, as I already said, the Q that we've defined for the quadratic is the same as the Q that we've already used in the f function. So we can express the quadratic in terms of the product of two root factors. Here's the exact result, retaining the f. And here it is, the same two factors in terms of the Q and the corner frequency of the original quadratic. The special case of Q of 0.5 means you have two equal real roots, which is the boundary with the complex root case. And we know that f is equal to 0.5 if Q is 0.5. This allows you to factor the quadratic into two equal real roots, which means that you would be 6 dB down at the corner frequency, consistent with the fact that that's also the value of Q. The interesting part comes in when Q is much less than 0.5. Because now, making use of the real root approximation, position this a little better. If Q is much less than 0.5, you can take f approximately 1, and here's the bonus. Look how simple those two real roots become. Q times omega 0 over Q. So visualize now the spectrum of values. If Q is high, you get complex roots, you get a peak. If Q comes down, the peak comes down. You go through a transition at Q of 0.5, two equal real roots, and if Q drops below 0.5, those two real roots simply spread equidistant on both sides of the original corner. Equidistant because it's a log scale, and one of them is Q times the corner, the other is 1 over Q, so that's why they spread equally on both sides. Now remember, f is close to 1 as long as Q is a long way below 0.5, but a long way doesn't really mean very far. Remember from the little graph of f, if Q is even 0.3, f is 0.9, so you're pretty close. You've only got a 10% error even so. So this illustrates graphically now what a small fuzzy area there is where f varies from 0.5 to 1. And it's a very small range of Q. That's why you can say whenever Q is small enough, it's a good approximation to take f equal to 1 and get this very simple answer. So, to summarize that, here's the typical case for the two ranges. One, when Q is large, keep the quadratic because we know the significance of Q in determining the value as it goes through the corner frequency. On the other hand, if Q is small, use the real root approximation, factor the quadratic into the two real roots, Q omega 0 and omega 0 over Q. Again, looking ahead to the design application, which is the only thing that's important. you may want to design the quadratic so that it does have low Q's, which enables you to fix those corners where the specification requires. It tells you immediately what value of Q you have to put those corners in a certain position. Here's the same pair of cases and the phase graph. There's a little too much in this picture, especially in the notes that don't have the color. What it shows is the high Q case where you get a steep transition with an intercept defined as 5 to the 1 over 2Q times the corner frequency. As Q gets lower, that slope will get shallower and shallower. And as you go through the transition to real roots, you go through two equal real roots, which would be two minus 45 per decade phase asymptotes at the same frequency, namely a minus 90 degree per decade phase asymptote. As Q drops below that transition, the two corners separate equally on either side, each one taking the minus 45 per decade slope with it. So here's the one that goes to the left. There's the minus 45 per decade slope that goes with it. Here's the one that goes to the right, taking its slope with it. And initially there's a large overlap where you have the minus 90 part of it per decade again. And the lower the Q gets, the further those separate, the overlap eventually goes away. And you have the two completely isolated real roots, each with its own minus 45 per decade slope. So there's a summary of the salient features of the two cases for quadratic solutions, which applies not only to the RLC network, but of course to anything else that comes up with the same formula, which, as we'll see later, includes the problem of the crossover of the loop gain in feedback systems, even though there's no inductance in sight. One further little extension we can talk about right now. This is the quadratic we've discussed, namely the denominator quadratic that results from the RLC filter. It's a low-pass filter. Of course, the quadratic could very well show up in the numerator. And making use of the vertical inversion properties, we'd now have a pair of zeros. But the geometry remains the same. You can either have a complex pair of zeros if Q is bigger than 0.5, or you could have two real zeros. And the geometry separates them the same. The zeros would be Q omega 1 and omega 1 over Q. But the same thing also happens in inverted form. By reversing the frequency axis, here's a pair of inverted poles. The quadratic is still in the denominator, but the S terms are inverted. It's simply a redefinition of the variable. Instead of having normalized S over omega 1 as the variable, you have omega 1 over S as the variable. But the properties of the quadratic stay the same. And it simply corresponds to reversing the direction of the frequency axis. And again, you can get a complex pair or you can get a real pair. And the same if you make a vertical inversion of that. Now you have a pair of inverted zeros, either real or complex. So we have the full symmetry now, both for single poles and zeros and for double poles and zeros. Okay, all of that has come out of the voltage transfer function of the RLC network, and the next thing we'll go on to is the input and output impedances. Well, we talked about the voltage transfer function of the RLC low-pass filter. Now we'll go on to talk about the input and output impedances, which are usually important parts of the specifications to do with the filter. What you see here is the same circuit we're talking about, and we want to calculate input and output impedance. So the input impedance is just the sum of the three reactances in series. So in terms of the original circuit elements, This is what you get. And then you want to substitute the same normalizing quantities that we used before, namely the omega 0 corner frequency, the Q factor, and the R0. So when you make those substitutions, you can collect the final result into this form in terms of the normalized quantities. And once again, that's a long way around for doing it. And this allows me to make a new principle here about how to minimize the amount of work that you want to do, which is start over. We want to calculate two additional properties of a given system, having already done one of them, in this case the voltage transfer function, in which we found out that it was convenient to express the result in terms of the normalized quantities, because that's what defines the property of the transfer function we're talking about. So if we want to calculate different transfer functions, it's a reasonable assumption at the beginning that we're going to want the same normalized quantities in the answer. So we'll save some work by anticipating that, and before we write any equation at all for the new functions, let's get rid of the original circuit elements in the model and replace them in terms of the normalized quantities that we know we want in the answer. Get them in right at the start. Then you don't have to go through that substitution again when you already know what you want the result to be in. So the way to save some work here is the next time you want to calculate something to do with the circuit, replace the original circuit elements in terms of the quantities you want in the result, which you do simply by inverting the definitions of those quantities. So, for example, instead of writing R, we invert this one and write R0 over Q. Do the same thing with the inductance, except you can make even an additional anticipation here, because what we're going to want in the answer is not the inductance itself, but the inductive reactance, namely SL. So put that in as well. So the inductive reactance SL turns out to be R0 times S over omega 0. And similarly for the capacitive reactance, 1 over SC, that becomes R0 omega 0 over S. So that now, in the very first line, when you write the input impedance, you simply write down the sum of those three reactances, and immediately you see that the R0 is a common factor. And in one more line, by bringing out the omega 0 over S out front and putting it in the denominator, immediately you reconstitute the same quadratic that we had before in the voltage transfer function. This has been done now in 2 lines instead of 4. Simpler, shorter, and better. And the same thing with the output impedance. Output impedance calculated by looking in at the output with V1 0. So it's the parallel combination of the capacitor, which is R0 omega 0 over S, and the resistor and inductor in series. So that's product over sum. And once again, the R0 shows up immediately as a multiplier in front. Bring the omega 0 over S out front of the quadratic and reconstitute again the identical quadratic. There's a new factor in the numerator, which immediately becomes an inverted 0, 1 plus omega 0 over Q over S. So very quickly you build the pole zero forms for these other 2 quantities that you're interested in, input and output impedance. The next thing we want to do is look at the asymptote structures to see what the qualitative interpretation is for those quantities. And a convenient way to do that is by using the building block approach, that these functions are made up of building blocks that we already know all about separately. For example, in the input impedance, you can consider that to be made up of the product of three factors. R0 in front, which is a scale factor. Notice this is the reference value of the resistance, which makes the scale factor for the impedance. The second factor is the quadratic equation. We know all about the properties of the quadratic, and the only difference this time is that it's in the numerator instead of the denominator where it was in the voltage transfer function. But we know what the relationship is. It's a vertical inversion. So the quadratic can be interpreted simply as the reciprocal of the voltage transfer function. It's the same formula. And finally, there's the 1 over s term, which is the third multiplier factor. So we already know the shapes of all of those functions, and all we have to do now to multiply them together is to apply superposition on the double log scales. So the R0 is where we start. That sets the reference level. You could choose this as the reference resistance and draw the magnitude of the impedance in dB relative to the value of R0. Or you could choose any other value as reference to fix the 0 dB level. The important thing is that the entire impedance function is proportional to R0. Remember what that is again. It's a property of the L and C, the characteristic resistance of the L and C. And that sets the vertical scale of the entire impedance function. Okay, so the next factor is the reciprocal of the voltage transfer function. Well, here's the H that we already set up. Peak response, I'm sketching the case for high Q. I could equally well sketch the case for low Q with the two real roots, but I'm going to leave that for you to do as an exercise. So I'm sketching the high Q case. So we get a single phase transition placed by choosing the intercept frequency at 5 to the 1 over 2Q times the corner frequency. Okay, but we want not H, but we want 1 over H. So I can take away the detail, and 1 over H is the vertical inversion of that. Or turn it upside down. Now I have to match this relative to the original reference. So 1 over H starts at 0 dB, which is unity, and then I scale that to the R0, so I have to make the vertical position line up with the R0. And the R0 doesn't have any frequency significance horizontally, so it doesn't matter where I put that, so I'll just join it on horizontally with the same line. So that takes care of the first two terms now. Now I still have a third one to do. That is a single negative slope, minus 20 dB per decade, and a fixed phase angle of minus 90 degrees. Again, all I have to do is position this both vertically and horizontally to make it fit on properly with the picture that I've got already. Move this a bit further over. Okay, vertically, I position this because the frequency dividing the S is omega 0. So that's the frequency at which the magnitude of that function is unity. So I have to match that against the 0 dB level I've already have for the 1 over H. So I put the vertical position so that the omega 0 position horizontally lines up with the blue line. But this is the same omega 0 that I've already incorporated in the quadratic, and I've located that at the corner of the quadratic function. So I have to move this picture over until the omega 0s line up also. So now I have everything in the appropriate relative position, and since I'm going to multiply those three functions together, I simply add the asymptotes on the log scale. So at this level, it will stay at R0, but I've got a negative slope to add to it, so the combination will follow the orange line, which is the negative slope, until the blue line goes up at a double slope, which cancels the single negative slope, so the result goes up on a single slope. And finally, I add back in the high Q peak, which is only relevant near the corner frequency of the filter, which I had in the first place, but I dropped it out while I was doing the intermediate construction. So now I can just put it back in now that I have the answer. You do the same thing with the phase, because I simply add the phase angles from the three terms. The R0 doesn't have any phase angle. The blue line is the phase asymptote for the quadratic in the numerator, which is a phase lead now, 0 to plus 180. And then again a shift because of the constant minus 90 degrees, so the blue line shifts down to the red line. So that's the overall result. So the input impedance of the LC filter follows the red asymptotes, and you see it's the typical series resonance. The impedance goes to a minimum and comes back up, and the phase goes from minus 90 through 0 to plus 90. That's expected, that's familiar, but of course notice an additional useful piece of information here. The asymptotes intersect at the normalizing resistance R0, the characteristic resistance of the L and the C. The value of Q determines what the actual minimum is. So if you consider the same L and C, but a varying Q resulting from a varying value of the series resistance, what happens is the Q gets smaller, this minimum rises, but the asymptotes stay in the same place. So the minimum would get bigger, and if Q is 1, the minimum would actually go through that asymptote intersection. And if Q is less than 1, then the roots separate eventually into two real roots, and you'd have a horizontal line joining the two real roots, which would be at Q omega 0 and omega 0 over Q. So you can visualize that sequence of transition as the Q gradually gets smaller and smaller. At the same time, of course, the phase slope would get shallower and shallower and eventually would separate into the 245 per decade separate asymptotes. So there's an example of a graphical construction in which you build up more complicated functions by using the simpler building blocks. Now you can do the same thing with the output impedance. Here's the output impedance function. It's a little more complicated. This time the quadratic is back in the denominator, but there's an S term in the numerator, so the combination of the two of them can be identified as the reciprocal of the input impedance function that we just derived. We can keep those two terms together already, since we've already constructed that. So once again, all we have to do is vertically position it relative to R0 and include the third term, which is the inverted 0. So the approach now is, we've got the R0 scale factor, and now we have the reciprocal of the input impedance. And the input impedance we just solved is this. So I take away the overlay, take the numbers off it, and I have to find its reciprocal. So I turn that upside down, and all that's left to do is to position this vertically and horizontally to fit with the R0. And again, the asymptote intersection we already know occurs at R0, so the proper vertical position is there, where the apex is at the R0 level. And the omega 0 is wherever I want to put it, on the horizontal direction. So that takes care of the first two terms, and all I have to do is put the third term in. That's an inverted 0. So this means at infinite frequency the magnitude is 1, 0 dB, and as I come down in frequency, at the frequency omega 0 over Q, there'll be a concave upwards corner. I've already assumed that Q is bigger than 1 for this sketch, so this corner is lower than omega 0 for this case. And correspondingly, the phase graph is a plus 45 degree per decade slope centered on the value of the 0. So vertically, the flat part of this is 0 dB for its own function, so that has to line up with the R0. And again, the omega 0 of this function is the same omega 0 as is in the quadratic, so I have to line it up horizontally like that. So once again, all I have to do is add the orange and the blue lines, both magnitude and phase. And so now the result looks like this. You follow the blue line where the orange line is unity, and when the orange line curves up with the 0, that'll flatten out the low frequency asymptote. Same with the phase. Now I have a superposition of a second order single slope and a first order single slope plus 45 per decade, and the red line is the combination of those. And as before, I can restore the high Q peak again, surrounding the peak of the output impedance, and you get the familiar result that the output impedance is a parallel resonance that has a high peak value. Once again, the asymptote intersection is at R0 and stays fixed regardless of the resistance. The resistance determines only the Q, and that determines how high the peak is relative to the asymptote intersection. Notice the interpretation of the low frequency part, where it levels off is at a value R0 over Q, which is equal to the original resistance, which is of course what ought to happen, because looking back into the output with V10 at 0 frequency, the cap is open, the inductors are short, and you're going to see just the resistance R itself. That's what you'd expect. So the effect of the resonance is to cause the output impedance to peak up beyond its 0 frequency value, which is what you expect for the effect of the resonance of the RLC. So again, you get all of this information, the analytic result, factored pole zero form, the corresponding asymptote graphs, with doing practically no algebra at all, introducing the quantities you want in the answer right at the beginning, so you don't have to reintroduce them part way along, which is duplicating work unnecessarily. And the value of the result in terms of the asymptote sketches is you get all of the important information in a very concise form, which includes not only the obvious parts of it that we've mentioned to do with the series and parallel resonance, but also the quantitative part of it to do with the vertical position of the asymptotes and what effect the Q actually has. As I mentioned, I chose for these two examples the case of high Q in order to draw high peaks, and I'm leaving it to you as an exercise to repeat those two sets of constructions, but draw it for the low Q case. So the formulas won't be any different, and the only difference is that for low Q, the shape of the geometry will be different. You'll have two real roots instead of the high Q peak. But you can go through exactly the same graphical steps to construct the result. So there's another homework problem. Notice I'm stacking up homeworks on you at a greater rate now. So. The reason I'm emphasizing these simple building block constructions is because you have to practice the results for the simple cases before you can do the more complicated cases. Those are the ones that you're going to have to deal with in real life, of course. And in this particular sequence, the next thing we need to talk about is the loaded LC filter. So this is the same problem we had before, except now we've got a load resistance RL across it. This represents directly the problem that switching power supply people have to deal with. Every switching power supply has an LC filter in it of this kind. And of course there's going to be a load, otherwise there's no point in building the power supply. So obviously this is a much more realistic case than the unloaded filter. Now, we can do the analysis for this case as well, and in order to keep it as simple as possible, the approach will be, let's make the use of as much of the work we've done already as we possibly can. Let's get all the benefits from it, because we want to use as much of those results as possible. So, again, start out by inverting the definitions of the normalizing quantities. Get rid of the original R, L, and C in favor of the normalizing quantities. So the SL and the 1 over SC are just as they were before. Do the same thing with the resistance, but there's one more difference now. We're going to be dealing with a second resistor. So I've put an extra subscript on the first resistor and on its corresponding Q factor, just so I can relate the Q directly to that resistor, because I'm going to have an additional Q factor now. And I want to keep the Q without any subscript as being the general quantity. So I put a sub E on the original RE and on the corresponding QE. The reason for choosing the subscript is that it stands for effective. Again, because in a practical case, this resistor is probably not a discrete resistor, but it probably represents the winding resistance of the inductor, plus possibly some source resistance, and in the case of a switching power supply, it also includes some sort of averaged value of the switch and the diode on resistances. So its value is actually an effective combination of maybe a number of contributions. From the switching power supply point of view, the objective is always to keep the total as low as possible, because it represents efficiency loss. The load current has to flow through that resistor. Okay, now we've got normalized quantities in place of the original circuit elements, but we have a new circuit element. So it's to be expected that we could benefit from defining a new normalized quantity. Let's call it a Q factor. So let's call it a QL corresponding to the RL. So here's the definition of the QL. Now you notice it's defined upside down from the first Q. In other words, the RE is in the denominator in the first case. It's in the numerator of the second case. And I do that on purpose, in order for the interpretation of the symbols to be consistent with historical usage. That is, Q factors were originally defined in terms of tank circuits, where high Q means low losses, low damping, and big peaks. This is the case for the QE. The QE goes to infinity if the RE goes to 0, which is the limiting case of 0 losses. We want to make the QL consistent with that. We want infinite Q to be corresponding to 0 damping. But in the case of the load resistance, it's in parallel relative to the tank instead of in series. So you get 0 losses when RL goes to infinity, and that gets you back to the previous case. So that's the reason for defining the QL upside down compared to the QE. Both Q's go to infinity in the appropriate limiting cases of 0 damping. Now we're ready to write the expression. And that is done in 3 lines, treating it again as a voltage divider. There's a bottom impedance, which is these two in parallel, product over sum. The denominator has the same thing plus the series two elements. The objective is to get rid of the internal fraction and express the result as a ratio of polynomials in S, which gives you the second equality. And the final step is also the usual one. You'd like to make the polynomials have a leading term of 1, so you can identify corner frequencies. So in the denominator, you bring out the constant term, do the same in the numerator, that develops a ratio again. And now you're left with a ratio of two polynomials, both with a leading term of 1. So this is the standardized or normalized form of the result. The first thing to do when you're discussing a slightly more complicated case is just check that it reduces to the simpler case in the appropriate limit, which would be, if you let RL go to infinity, then QL goes to infinity. And what happens? The leading term goes back to 1, and all of these coefficients go back to 1, and this term goes back to 1 over QE, which is the same result we had before, so that's okay. Now, considering what the effect of the QL is, you can immediately identify what the influence of the RL is on the result. That is, how does it change the previous result? And you see that it does three things. It makes the leading coefficient non-unity. It makes it slightly less than 1. It also changes the corner frequency of the quadratic. Because what I really ought to do is define a new corner frequency, omega 0 prime perhaps, which is the old one multiplied by the square root of 1 plus 1 over QE QL. Because this entire coefficient determines the new corner frequency. So the effect of the loading is to change the corner frequency. In fact, it raises it. The QL does something else. It changes the coefficient of the middle term, which is 1 over the Q of the complete circuit. So there is now a total Q factor, QT, which is defined as this entire coefficient after you've separated out the changed corner frequency. So listing those three results, this is what the loading does. Changes the low frequency asymptote, and if you restore the original quantities instead of the Q's, obviously it simply represents the original resistive divider formed by the RL and the RE, because at zero frequency the cap opens and the inductor shorts. So that's all you're left with at zero frequency. Then the other two effects are the changed corner frequency and the changed damping coefficient. Now you can extract even more information out of this result. In the context of a power supply filter, again, dealing with a real inductor, you know what this zero frequency coefficient has to be. It has to be as close to 1 as possible. Because your objective is to make an efficient power supply, and the resistive divider effect of the LC filter is a direct factor in the efficiency. So to maximize the efficiency, you're certainly going to design the filter so that this ratio is as close to 1 as you can make it, which for a given load, of course, means you have to minimize the RE, which is the parasitic losses. Now, that's a useful piece of information, because you notice this same factor shows up in these other two effects. So if it is necessary that the filter have this ratio close to 1, it follows that these other two effects can be simplified. In other words, there will be a negligible change of corner frequency, because it's the same factor. Those two effects, therefore, can now be relegated to second-order effects due to the loading. Second-order effects are supposed to be negligible in any filter that's going to be useful. Because if you don't satisfy that condition, throw away the filter and start over. So that's the first additional result. Now there's still a third effect of the damping, of the loading I should say. And that doesn't go away with the same restriction, but it gets simpler. Because again, it has the same factor showing up, but that isn't the only thing that happens. So you can make this factor essentially 1, and what you're left behind with is 1 over QE plus 1 over QL, which is the same thing as defining a new total Q factor which has this derivation in terms of the other two. In other words, it's reciprocal sums, and it's just like the parallel combination of the two contributions. So, subject to neglect of these two second-order effects, the voltage transfer function of the loaded filter is the same as the unloaded filter, except it has a total Q factor which is lower than either of the two contributions, and quantitatively is equal to the parallel combination of them. So that's a very simple result. You've reduced it to the simplest possible case, which is useful for practical purposes. Now, once again, a lot of textbooks have this stuff in it. Very few of them use these normalized quantities, and I don't remember seeing anywhere this simple, useful parallel result. Although a lot of people, of course, know it because they found it out along the way. But you see, it's very simple to set it aside, to expose it as a basic property of the system. And just to try to emphasize that again, if you consider the original filter, and you do the analysis in terms of the original circuit elements, instead of substituting immediately the normalizing quantities, this is what you get. And most people would stop at this point. Say, this is the answer. Of course, it's correct, but it doesn't much help. Because what you don't get from this is the fact that the loading does three separate things, two of which are second order, and the third one is this most useful result of all of this parallel combination of the Q factors. In this version, you don't even see any Q factors. So this is another good example of the fact that the high entropy form isn't of any value, especially when you have to invert the whole thing in order to do a design. Now, all that I've done in the remaining lines is get the low entropy form the hard way, by starting with the high entropy version and then applying mental energy to identify these normalizing quantities again. And you can indeed push the answer down into the low entropy form, but what a lot of work that is. Plus the fact that you have to think about doing it in the first place, and you have to think at each line, what do you need to do next? So how much better it is to introduce those quantities in the first place, and then it all happens automatically. So clearly that's the better way to do it. Well, that's the voltage transfer function of the network, and once again with the loaded filter we're going to need to know input and output impedances. So that's simply a repetition of the same processes we already did, except taking into account some additional complications because of the load. First, the graphical result for the voltage transfer function. The only difference is you lower the total Q factor, so it doesn't peak quite as high, neglecting second order effects, which at the same time means that the phase asymptote simply comes more shallow because now the intercept is at 5 to the 1 over 2 QT instead of 5 to the 1 over 2 QE. So it's just shallower. Now, for the input and output impedance, again, of course, start with the normalized quantities. Input impedance is the sum of the various elements, and again, in 3 lines, you get the full result, in which you have the full quadratic, which is moved again to the numerator from the denominator. So you get the same 3 effects that we had before, 2 of which are second order, which means you can simplify the quadratic to the same earlier version. You make the leading coefficient unity, and the only first order effect in the quadratic is the total Q factor comes out again as the parallel combination of the 2 contributions. This time there's a second first order effect. There's a new corner frequency, an inverted pole in the denominator that was not there in the unloaded case. And again, if QL goes to infinity, that corner goes away. Then it reduces to the previous case. So what is the physical interpretation of the presence of this additional inverted pole? Now, relative to the rest of the function, which stays the same, the appearance of an inverted pole means simply that something else is going to happen as you go towards low frequencies. What is it that happens? Well, look back at the filter. Consider the input impedance evaluated at very low frequencies where the inductive reactance approaches 0, the capacitive reactance approaches infinity. Does it make any difference to that result whether or not the RL is there? And the answer is yes, it makes a big difference. Because if the RL is not present, the input impedance is dominated by the capacitor that goes to infinite reactance. So the input impedance goes to infinity towards 0 frequency. If the load resistance is there, obviously that puts a limit on how high the impedance can get as you go to 0 frequency, and obviously it has to level out at RE plus RL. So there is a change of asymptote slope as you go towards 0 frequencies, depending on whether or not the load resistance is there. If there is a change of slope, then there must be an additional corner frequency. And the inverted pole is the frequency that describes that. So, making the same second order approximations, simplifying the quadratic, making the leading coefficient unity, reduces the result now for the high Q case to the simplified quadratic in the numerator with the R0 coefficient, and you have an additional inverted pole. And graphically, the result looks like this. In the unloaded case, the asymptote went to infinity at 0 frequency. Now it levels off because of the inverted pole. And the only other difference is a lower Q factor. The inverted pole will have an additional phase asymptote, which by superposition will bring the phase back from the original minus 90 degrees from the infinite asymptote, brings it back to 0 at 0 frequency. So that's the input impedance of the loaded filter. And we do the same thing with the output impedance. Again, in 3 lines, you get the full result. The full quadratic again, it's exactly the same quadratic as you had in the previous cases. So you can simplify that. So the quadratic goes back to the simpler form. Leading coefficient goes to the R0. This time there is no additional corner frequency resulting from the loading. That is also consistent with what you would expect just from looking at the circuit. The output impedance is found by making V1 0, so you have the parallel combination of three branches. Go towards zero frequency. Does it make any difference whether the RL is there or not? If you go to zero frequency, the inductor becomes a short and you have the very small RE right across the output. The RL is much larger than that, and it makes no difference whether it's there or not, or even if you account for it, it doesn't change the slope. It's still flat. It's still a resistance at zero frequency. So there's no change of output impedance, asymptote, slope at zero frequency. Therefore, loading it does not introduce any additional inverted zero or inverted pole. Now you ask the same question at infinite frequency. At infinite frequency, the inductor opens, takes away that branch, the capacitor goes towards the short. Does it make any difference whether the RL is there or not? No, it doesn't. If it's across a short, it makes no difference. So there is no change of output impedance, asymptote, slope towards infinite frequency, therefore no new normal pole or normal zero. Consistent with the result. Analytically, no additional poles or zeros of any kind caused by loading. So the only difference in loading the filter as far as the output impedance is concerned is it lowers the Q factor of the quadratic. So here's the output impedance, and lowering the Q is the only difference. Okay, the things I've tried to illustrate there is we're trying to work towards more complicated problems, which are the ones you really have to deal with, and the guidelines here are always keep it simple. Don't put any more in than you need. Set things up in low entropy form right from the start. Because then useful conclusions, such as the three effects, two of which are second order, then the useful conclusions just stand out and hit you. Whereas if you do it in high entropy form, those things remain buried and you never even see them. Now the payoff of all this is the next step. A still more complicated case, which is the loaded RLC filter with the presence of yet a third damping resistance in series with the capacitance, which in real life, of course, is associated with the ESR of an electrolytic. Again, this is, of course, particularly relevant to the power supply case. So now, following the same procedure, if we want to know the three functions, voltage transfer, input and output impedance, for the case of the LC filter with three sources of damping, first thing is again introduce the normalizing quantities right from the start and define a third Q factor corresponding to the added resistor. So now we want a QC related to the RC. So we have the choice now of which way up shall we define it. Should we define it like the QE or like the QL? And the answer to that question is it depends on what is the position of this resistor relative to the LC tank. And you see that it's in a series position relative to the LC, just like the RE was. So the appropriate way to define the QC is the same way up as the QE. Infinite QC will occur when RC goes to 0, which takes you back to the previous case. Now we could go through the analysis of this circuit, same as we did with the others, and it'll be still more complicated this time. So now let's try to short circuit that altogether. Based on what we know of the previous two cases and what the effect of the additional damping resistance was, let's just try to guess what the answer is going to be in this more complicated case. Now, notice you don't very often tend to think this way. You're used to starting with complicated cases and then seeing what happens when you simplify it. But it's much more useful, much more valuable to be able to do that in the other direction, to use a simple analysis and make a quantitative answer that's more complicated without actually deriving it. Let's see if we can do that for this case. Of course, you're going to pay a price if you're trying to generate a more complicated result by guesswork. The price we're going to pay in this case is that we're going to neglect the second order effects before we even start. So we're going to assume that there's no change of corner frequency, no change of zero frequency asymptote, and the only thing we're going to look for is first order effects, which will be the total damping and possible new corner frequencies. So let's do the voltage transfer function first. Assuming the second order effects, we're going to get a quadratic in the denominator with the same corner frequency, omega 0. And there'll be no change of zero frequency asymptote. What's going to be the effect on the Q factor? Well, it's a pretty good guess that it's going to be the triple parallel combination of the three constituent Qs, since that's what happened when we added the second one. Now, of course, that's a guess, but I think it's a pretty good one. And in line with our entire philosophy about doing analysis, make every assumption and approximation you can to begin with, plunge ahead and get an answer any way you can, and then go back and see if it's okay. So that's simply the same thing that we're doing right here. Let's make a guess that the total Q factor is a triple parallel combination. So that takes care of everything now except the possibility of new corner frequencies. But I've already mentioned how we check the effect of the analysis in the previous cases. So we can use the same qualitative argument of simply looking at the circuit and asking, is there any change of slope of the asymptotes at zero or infinite frequency for the three functions? If there is a change of asymptote, then you know there's a new corner. So in this case, we're looking at the voltage transfer function. Take zero frequency. The cap is open. Does it make any difference whether the RC is there or not? No. It's in series with an infinite impedance. Makes no difference. Therefore, there is no additional inverted pole or inverted zero resulting from that resistance. Go to the other extreme. As frequency approaches infinity, inductive reactance increases, the RE drops out. The capacitive reactance decreases. The RL drops out. So you're left basically with a pure LC filter in the absence of the RC. And that's what gives you the double slope, the LC filter, because you get an S from both of those elements towards infinite frequency. So the question remains, if you put the RC in there, does that make any difference to the infinite frequency slope? Yes, it does. Because at a high enough frequency, the capacitive reactance drops below the RC, and the capacitance drops out, and you're left with the RC. That's a significant difference from the case where RC is zero. In fact, what happens is the LC filter becomes an LR filter, which is a single pole function. Therefore, the final infinite frequency asymptote, instead of being a double slope, has to come back to being a single slope, which means there must be a concave upwards corner, so there must be a normal zero. So write it in. There's the normal zero. And you even know quantitatively what it is, because the value of the zero is where the slope changes, which is the corner frequency where the capacitive reactance equals the RC, which in terms of the normalized quantities is QC times omega 0. So that's the answer. This is a quantitative result obtained for a more complicated circuit without doing any algebra at all. So that's sort of the ultimate in low entropy. The best kind of algebra is no algebra at all. But still, you see, a quantitative result. Okay, you can do the same thing, of course, for input impedance. Neglect second order effects. The total Q factor, again, will be the triple parallel combination. Look for new corner frequencies. At zero frequency, the input impedance is dominated by the RL. Capacitor is open, makes no difference whether the RC is there or not. No additional inverted pole or zero. Go to infinite frequency. The input impedance is dominated by the inductor. The capacitor goes to zero, and whether you're left with an RC or not, in series with an inductive reactance that's going to infinity, again the RC makes no difference. So there's no additional normal pole or zero. So again, you can build a quantitative result by extension or extrapolation. I'd like to say inductive reasoning, but that word unfortunately gets confused with the physical inductor. But anyway, it's an extension of the reasoning without actually doing the algebra. Notice again the usefulness of the symmetry between normal and inverted poles and zeros. That's what enables you to make these arguments to do with zero frequency asymptotes as well as infinite frequency asymptotes, which covers all the possibilities. Well, there's one more. Well, here's the results for the two we've done already. Voltage transfer function. Q factor is lowered because of the ESR of the capacitor, which also introduces an additional normal zero. Input impedance, the only difference is the change of Q factor. So I've written down here the principle that you use in making these arguments to build up more complicated functions. And there's one I didn't do, so I'll leave that again for you to do as an exercise. Build the factored pole zero form quantitatively for the output impedance of the loaded LC filter in the presence of the capacitor ESR, just by following those same arguments. Now, once again, and I keep hitting this because I can't overemphasize the importance and the value of the low entropy forms involving these normalized parameters. It's because the shape of the functions that you get, which are the things you have to design to meet specs, are clearly exposed in terms of those normalizing parameters. That's why it's important to have them in the answer, so you can work backwards and do a design. And all of this is very elementary, simple stuff. This is even passive circuits, see, which you deal with in the very first linear circuit analysis course that you ever do. But somehow or other, this translation to normalized quantities just doesn't catch on, or it isn't even taught in the first place. And people go out into industry, and they do designs, and they even do research, and they write papers. And sometimes I get these papers to review. And here is one page out of a manuscript that I got not too long ago. And it's to do with the output impedance of a damped LC filter, exactly the one we've been talking about, except a little simpler. It has the ESR there, but not the load. And this is the algebra that appears in the paper. Now these T's are various loop gains, and it doesn't matter much what they are. The thing to look at right now is this one. This Z is the output impedance of that network. And see how he's written it. It's the ratio of polynomials. The bottom one has a leading term of 1, but the other one doesn't. They're both quadratics. He hasn't even noticed that the numerator 1 factors exactly. What is the reference value for the impedance when you express the result as a ratio of polynomials? The reference value is the zero frequency value, which is what you get when you let all the S terms go away. What do you end up with? RL1. So he's got RL1 effectively as the reference impedance at the front end, which is the zero frequency impedance. That's correct. But what is it he wants to do with this? Look what he says under here. You can't read it? No. Well, it doesn't matter. I'll just say what it is. At the resonant frequency of this filter, the impedance Z, its output impedance, will attain a very high value. And that's what he's concerned about in the whole paper, is the maximum value of this output impedance. Limited only by the series resistances RL1 and RC1. Where's RC1? Well, it's buried in here somewhere. So what he's interested in is the peak value. What he's got as the leading coefficient is the zero frequency value. So the thing that he's really concerned about is how big that maximum can get is totally obscure. So the equation tells you nothing. So that's bad enough. And just to mention briefly what the other stuff is, these are to do with various loop gains of a regulator that contains this filter. And these lines that I drew around it indicate buried parameters. Notice this Z is in here, it's in there, it's also in the delta, which also appears here and here. And and this A1, what's this A1? Well, A1 is this long mass, which is part of this bigger mass, which is part of the delta. And my point about all this is, it's worthless. You see, he's written all this stuff in the paper, and what is important about it is in one sentence that doesn't come out of the equations. So he might as well not have bothered to write them. And you certainly are not going to get anywhere with design in trying to work any of these backwards. So that's my final word for the moment on the importance of low entropy expressions and keeping things simple and building up more complicated cases out of simpler pieces.